dear students, so far we have discussed about linear programming problems. When I say linear programming problems, the objective function is in linear form and the constraint also in the linear form. But in this lecture, I am going to discuss about nonlinear programming problems, that is called nonlinear optimization models. So, what is the meaning of this nonlinear optimization? For example, when I write say maximize, for example, maximize z equal to say 5 x 1 square plus 2 x 1, you see that the power of x 1 is more than 1, 2. So, now I can call it, this objective function is nonlinear form. Similarly, say this is subjected to say 3 x 1 square plus 2 x 1 say less than or equal to 20. Now, what is happening here? The constraint, okay. In the constraint also there is a nonlinear form. So, this kind of problem is nonlinear programming problems. So, in this lecture what I am going to discuss, I am going to explain what is unconstrained optimization, then constrained optimization, then I have taken a sample problem on nonlinear context, then that I have solved with help of solver. Introduction. Many business processes behave in a nonlinear manner. So far the basic assumptions for our linear programming model is the objective function and the constraint should be in the linear form, but that is not the case. For example, the price of a bond is a nonlinear function of interest rates, because interest rate is not in the linear form, it is a nonlinear form, and the price of a stock option is a nonlinear function of the price of the underlying stock. Another example is the marginal cost of production often decreases with the quantity produced. So, the rate of decrease is in the nonlinear form. Okay. Another example, the quantity demanded for a product is usually nonlinear function of the price. Okay. See, we see the law of demand is like this. Here is price in quantity. The law of demand says in the linear form, but in many situations it won't be in the linear form, it will be in the nonlinear form, it may be like this, like this. Okay. So, these and many other nonlinear relationships are present in many business applications. Then what is nonlinear optimization? A nonlinear optimization problem is any optimization problem in which at least one term in the objective function or a constraint is nonlinear. If any in one term, as I explained previously, if it is in nonlinear form, then we can say it is nonlinear optimization problem. This picture is an example of a nonlinear form. What is a linear form? Linear form is straight line. We introduce a constraint and unconstrained nonlinear optimization problem by considering an extension of the PAR incorporation linear programming problem. This problem is taken from the book Anderson et al. Already we have solved this problem in the linear form. Now, we are going to modify that problem in a nonlinear context, then we are going to solve it. So, the first one is called constrained and unconstrained nonlinear optimization problem. If there is no constraint in the objective in the problem, then we can say it is unconstrained nonlinear optimization problem. That means there will be only objective function. If you incorporate, if you include constraint into the problem, then we can say it is called constrained nonlinear optimization problem. First we will discuss about an unconstrained problem. What is the meaning of unconstrained? There will not be any constraint. Okay. Let us consider the revision of the problem which you have discussed. So, that company decided to manufacture standard and deluxe golf bags. In formulating the linear programming model for the problem we assumed, it could sell all of the standard and deluxe bags it could produce. That was the basic assumption in the LP model. What is that? Whatever they produce, that will be sold in the market. However, depending on the price of the golf bags, this assumption may not hold, because we know that law of demand, there is a inverse relationship between price and demand. So, an inverse relationship usually exists between price and demand. This was the problem. What is that problem? Maximize 10S plus 9D. Their company produces 2 bags, one is the standard bag and deluxe bags. There was a 4 constraint: cutting and dyeing constraint, sewing constraint, finishing constraint, inspection packaging constraint. This was the original problem. Now, we are going to modify. What we are going to modify? Only in the objective function we are going to introduce the concept of nonlinearity. What is that? As price goes up, the quantity demand goes down. That is what the law of demand says. What is that one? If this is price, this is quantity. If the price goes up, the quantity demanded goes down. Let PS denote the price that company charges for each standard bags. Okay. The price of your standard bag is called PS, and PD the price of your deluxe bags. Okay. Assume that the demand for standard bag S and the demand for deluxe bags is given by these equations. This is called your demand function. What is the demand function? Which connects your quantity and the price. So, S equal to 2250 minus 15 PS is the demand function for the standard bag. D equal to 1500 minus 5 PD is the demand function for the deluxe bag. Now, we are going to find out the profit contribution of the standard bag. The revenue generated from standard bag is the price of each standard bag, okay, PS times, and the number of standard bags it is sold. So, what will happen when you multiply price and the number of bags sold? So, you will get the revenue. From the revenue, when you subtract the cost, you will get a profit contribution. If the cost to produce a standard bag is say $70, okay. So, the profit contribution for producing and selling, okay, S number of standard bags is equal to revenue minus cost. What is the revenue? Price multiplied by demand of standard bag minus this cost multiplied by demand of standard bags. So, the profit contribution is, so this component is revenue, this component is the cost. So, this will give you the profit contribution for the standard bag. Similarly, okay, we can solve the above equation for PS to show how the price of the standard bag is related to the number of standard bags sold. How? For example, I will come back how we got this relationship. For example, we know the demand function for the standard bag is S equal to 2250 minus 15S. From this, I can find out PS. What is the PS? The price of the standard bag. So, when you bring on the left hand side, 15 PS equal to 2250 minus S. Then when you simplify PS, okay, the whole component has to be divided by 15. So, 2250 divided by 15 minus S by 15. So, that will be equal to 150 minus S upon 15. That is what we got. PS is 150 minus S upon 15. Now, we are going to substitute this PS. Okay. So, substituting 150 minus 1 upon S upon 15 for PS in the previous profit contribution margin for S in the equation, the profit contribution for the standard bag is, we know already the equation for profit contribution of S. So, instead of this PS, we are going to substitute this 150 minus S upon 15. So, then if you 150 minus S upon 15, then you multiply 150S minus S square upon 15 minus 70S. Again, if you further simplify, so 150 minus 70 is 80S minus 1 upon S square upon 15. So, this is the profit contribution of our standard bag. Similarly, we can find the profit contribution for the deluxe bags. How? We know, suppose the cost to produce each deluxe golf bag is say $150. Again we will come back to the finding profit contribution for the deluxe bag. So, profit contribution is revenue minus cost. What is the revenue? Price multiplied by quantity sold or demanded minus cost of the product. So, here what we are going to do, from our demand function, we know our demand function is D equal to 1500 minus 5 PD. If I simplify, when you bring on left hand side, 5 PD equal to 1500 minus D, then PD when you divide by 5 on both sides. So, 300 minus D upon S. So, instead of this PD, I am going to substitute 300 minus D upon 5. So, when I substitute here, when I again simplifying, I got this result. What is this result? 150 D minus D square 5. Now, this is the profit contribution for deluxe bag. Previously, we got profit contribution for standard bag. Now, we got for the deluxe bag also. Now, we are going to substitute this one, then we can find out the total profit contribution of standard and deluxe bag. So, the total profit contribution is the sum of profit contribution for standard bags and the profit contribution for deluxe bags. Thus, the total profit contribution is written like this. What is that? So, the total profit contribution of standard bag and deluxe bag is equal to 80S minus 1 upon 15S square plus 150D minus D square upon 5. This function is an example of quadratic function because the nonlinear terms have a power of 2, because the power is 2, then we can say it is a nonlinear function. Again I have brought this is a quadratic function. This is objective function is nonlinear form. Now, you see that we are not going to consider any constraint here. Now, with the help of solver, I am going to solve this equation. What is that equation? 80S plus 150D minus S square upon 15 minus D square by 5. Now, I am going to solve this function, that is this one, that is maximize 80S minus 1 upon 15 S square plus 150 D minus D square upon 5. Look at the formulation in Excel. So, I have written S in D5 I have written the coefficient of S. Similarly, in E5 I have written the coefficient of D. Then in F5, when I click F5, the coefficient of S square is 1 upon 15. If I click F5, see that it is 1 upon 15. Similarly, if I click G5, you see this is 1 upon 5, it is a 0.2. Then look at the value of F6. F6 is that is a square of D6. Then similarly, G6 is it is the D square, that is square of your E6. Now, if I click an objective function, the K3, see this. So, what I have done, sum product of, first I am multiplying the coefficient of S, minus, because both the squared term has the minus, sum product of the linear function minus sum product of nonlinear function, that will be value of my objective function. So, what point I want to say is, we are optimizing only the S, we are not bothering about the S square. So, here the changing cell is only in the S and D, which is linear form. Now, if we go to solver, home, data, solver. So, the value of objective function is K4, this is maximization problem. The changing cell is, it is only D6 and E6, only the value of S and value of D. And note that there is no constraint here, because this problem is unconstrained, we are not going to consider the constraint. Then you see that I am selecting a method called GRG nonlinear instead of simplex. There are different options there, simplex and nonlinear. So, I am clicking nonlinear. Then when I solve it, yes, you see that I got the value of S is 600, the value of D is 375. So, the value of objective function is 52,125. This is the way to solve an unconstrained optimization problem. Now, I will interpret the solver's output. So, using a computer solution method such as Excel solver, we find that the value of S and D that maximizes the profit contribution functions are S equal to 600 and D equal to 375. So, the number of unit that should be sold for standard bag is 600 and for deluxe bag is 375. So, when we substitute this value in our demand function, okay, we will get the value for our PS and PD. What is the PS? The price of the standard bag. For example, the price of the standard bag will become 110. The price of the deluxe bag will become 225. Then the profit contribution will be 52,125. So, these values provide the optimal solution for the problem which you have considered if all production constraints are also satisfied. But at present we did not consider the constraint because it is an unconstrained problem. Now, I am going to explain how to use solver for solving a nonlinear equations, okay, where there is no constraint. For example, the problem is like this: find the value of x and y that minimize the function. The previous problem is we consider the maximization problem. Now, we are going to we have to find the value of x and y which minimizes this function. What is this function? X square minus 4x plus y square plus 8y plus 20. Here we are not going to consider non-negativity constraint. So, what it says that do not assume non-negativity of x and y. So, if the problem is like this, how to use solver? Okay. So, now I will go to the solver, I will explain how to solve this equation. Now, the equation for which we need solution is this one. What is that? X square minus 4x plus y square plus 8y. First I have written only the value of x and y. The coefficient of x is minus 4 I have written, the coefficient of y is plus 8 I have written, then the coefficient of x square is 1 and the coefficient of y square also 1 plus 20. Okay. Now, you see how I am writing the equations for this. So, if I click C3, see that C3, that is the cell where I am going to get the value of x. Similarly, the D3 is the place where I am going to get the value of y. Now, if I click on E3, see that E3 is the square of x, that is C3 square. Similarly, F3, see that is D3 square, that is nothing but the value of y square. Now, but there is one constant also is there 20. Now, I am going to incorporate this 20 into my objective function. Now, you see this sum product, the linear combinations plus sum product, the nonlinear combinations plus 20. So, the constant is I have added into the objective function itself. Now, I go back to the solver data, solver. Okay. Now, you see that the minimization function, the variable cell is C3 and D3. So, I am going to solve nonlinear. You see that I did not check this box. So, that means I am allowing to get a negative value also. When you check this box, you will get only positive value. Okay. So, now I can get the negative value also. When I solve it, yes, now you see the value of C3 is 1.99, that is a 2, and value of D3 is minus 4. Okay. So, this is the method to solve a nonlinear equation with help of a solver. Now, I got the value of x is 1.99, say x equal to 2, the value of y is minus 4. This is one example how to use solver. Now, we are going to see the second category, that is called a constrained problem. See, unfortunately, that company cannot make the profit contribution associated with the optimal solution to the unconstrained problem, because the constraint defining the feasible region are violated. How it is violated? We will see that, because previously we did not consider the constraint. For instance, the cutting and dyeing constraint is like this: 7 upon 10 s plus d less than or equal to 630. We got the value of s and d. What is the value of s? Is 600, value of d is 375. But when you put the total, it has become 795, that is against our constraint. How much? Our limit is 630, but it is exceeds 165. Okay. Now, the value of 600 and 375 is lying here, but our feasible region is this region. Okay. Now, the solution which I have considered 600 and 375 is not optimal solution, because it is violating our constraint. So, now what we are going to do? We are going to consider all the constraint, then again we are going to solve this problem. Such problem is called constrained nonlinear optimization problem. Okay. So, the feasible region for the original problem along with the unconstrained optimal solution point, for example 600 375 for this objective function is like this, that is it is violating our constraint. Okay. Now, what I am going to do? I am going to consider all the constraint and this objective function. Again I am going to solve with the help of solver. First I will explain the formulation of this problem into the Excel. So, I have written value of s and d, then I have written coefficient of objective function 80s, please see this 80s plus 150d minus 1 upon 15s square, similarly minus 1 upon 5d square. So, the d6 is the value of s, similarly e6 is value of d, but the f6 is the value of s square, similarly g6 is value of d square. As usual, I have written all the other constraint, because look at the bottom, all the constraints are in the linear form. Okay. So, again I have written suppose if I click on F8, for example F8, you see that sum product D6 to E6 and D8 to E8. Okay. Because in the constraint there is no square, there is no nonlinear form. So, I am considering only the linear form. Now, you look at the objective function, the K4. The K4 sum product for positive coefficients, that is for linear coefficients, minus sum product for nonlinear coefficients. Okay. Now, if I go to solver, data, solver, yes, this is a maximization problem. Then the changing cell is D6 to E6. Here you see that I am considering all the constraint. So, now it will become a constrained nonlinear optimization problem. So, when I solve it, yes, now I am getting the value of objective function is 49,920. Then I got the value of s is 459 and the value of d is 308. Okay. Now, I will interpret this result into the lecture. Now, I have brought the solution for the nonlinear problem. What is that? I got the value of s and value of d and the value of objective function. You see that the value of objective function is decreased when we consider the constraint. Previously it was above 50,000. Now, by considering the constraint, the value of objective function is decreased. So, this maximization problem is exactly same as the problem which we have discussed in the previous lecture, except the nonlinear objective function. So, the optimal value for the objective function is $49,920. The variable section shows that the optimal solution is to produce 459 standard bags and 308 deluxe bags. Here we can interpret the meaning of slack and surplus also. Here all the constraints are less than or equal to type, then we can say all the variables are slack variables. So, similar to our linear programming problem, in the slack surplus column of constraint section, the value of 0 in constraint 1 here means that the optimal solution uses all the labor hours in the cutting and dyeing department, but non-zero values indicate that the slack hours are available in other departments. So, the interpretation of slack is similar to what we have interpreted in the LP model, linear programming model. Now, we will analyze this solution. See, when we not at all consider any constraint, the value of objective function is this one 52,125. You see that this is an ellipse shape, but now we got that the optimal solution is here when we consider the constraint. There is another constraint also there, that is a 45, there is another ellipse also appearing when the value of objective function is 45,000. So, the value of objective function is 49,920, where it is intersecting on the feasible region, this point. So, this point is our optimal value for a nonlinear problem. We will interpret further in coming slides. You see, the graphical view of the optimal solution of 449 here, this point is 459 comma 308, which point? This point, this point. The optimal solution uses all the labor hours in the cutting and dyeing department, but non-zero value indicate that slack hours are available in the other departments. Note that the optimal solution is no longer at extreme point of the feasible region. When we solve a linear programming problem, the optimal solution was lying on the corner point, but that is not the case here in the nonlinear problem. So, the optimal solution lies on the cutting and dyeing constraint 7 upon 10 s plus d equal to 630, but not at the extreme point formed by the intersection of cutting and dyeing constraint and finishing constraint, or the extreme point formed by intersection of cutting and dyeing constraint and inspection packaging constraint. So, what we are understanding here, the optimal solution need not lie on the intersection points or the corner points. The optimal point may lie anywhere. Sometimes the optimal point may lie inside the feasible region also, that we will see in the next slide. In the figure we see 3 profit contribution contour lines. So, these ellipse is nothing but contour lines. The meaning of contour line is all the points on the contour points will provide the same value of objective function. So, meaning is each point on the same contour line is point of equal profit. Here the contour line show the profit contribution of 45,000, this one, 49,920, this one, and 51,000 of 500, this one, 51,500. In the original problem described in earlier lectures, the objective function is linear and thus the profit contours are straight line. Previously in the linear models, the profit lines are linear, but now the contour lines are linear, but now the contour lines are not linear. However, the problem with the quadratic objective function, the profit contours are ellipses. That is a point we have to note here. Because part of $40,000 profit contour lines cuts through feasible region, we know that the infinite number of combinations of standard and deluxe bags will yield the profit of 45,000. So, when we say the 45,000s, there may be infinite number of combinations of our S and D. Okay. Similarly, an infinite number of combinations of standard and deluxe bags also provide when the profit function is 51,500. However, none of the point when the value of objective function is 51,500 here, this one, none of the point the contour profit lines are in the feasible region. It goes beyond the feasible region, as the contour line move further out from the unconstrained optimum. This is the unconstrained optimum value. So, the profit contribution associated with each contour line decreases. You see, initially our solution was this one. When we move away from this unconstrained optimal values, the value of objective function is decreases. But where it exactly touching, when it is touching this point, we got the maximum value for the objective function, that is 49,920. This 2 point, that is the value of S and D, is our optimal solution. The contour line representing a profit of 49,920 intersect the feasible region at a single point, this point. Okay. So, this solution provides the maximum possible profit. How much? 49,920. No contour line that has the profit contribution greater than 49,920 will intersect the feasible region. Because the contour lines are nonlinear, the contour line with the highest profit can touch the boundary of the feasible region at any point, not just an extreme point. The extreme point was the case of linear programming problem. It is also possible the optimal solution to a nonlinear optimization problem to lie interior of the feasible region. Another important point should be noted. It is not necessary on the boundary. Sometime your optimal solution may be inside the feasible region. For instance, if the right hand side of the constraint in the problem were all increased by a sufficient amount, the feasible region would expand, so that the optimal unconstrained solution point, that is 600, 375 in the figure, would be in the interior of the feasible region. So, what is happening if the constraint right hand side is increasing? What will happen? The feasible region may become like this. When the feasible region become like this, our optimal solution lies inside the feasible region. Okay. That is the point which I am trying to say. Many linear programming algorithms, for example simplex method, optimize examining only the extreme points and selecting the extreme point that gives the best solution value, but that is not the case for nonlinear problem. As the solution to the constrained problem, okay, what we have discussed in the nonlinear context, that method will not work in the nonlinear case. Which method? Finding the extreme point, then that will be the optimal solution. Why? Because the optimal solution is generally not an extreme point solution. Hence, nonlinear programming algorithm are more complex than linear programming algorithms. The important point I want to emphasize here, the scope of this lecture is not on the different algorithms. So, fortunately, we do not need to know how nonlinear algorithm work, we just need to know how to use the different algorithms, especially in the management context. Okay. We should know how to use this algorithm. So, computer software such as Lingo, Excel solver are available to solve nonlinear programming problems, but in this course we are going to use only Excel solver for solving nonlinear problems. Dear students, in this lecture I have discussed about the concept of nonlinear optimization problem. So, what I have discussed here is, I have discussed about what is an unconstrained optimization problem where there will not be any constraint at all. Then I have discussed about the constrained optimization problem where we will consider different constraints. Then I have taken a sample problem that I have explained with the help of solver how to get the solution. Then I have interpreted. Thank you very much.